Welcome to Understand the Math. In this Calculus 1 video, we're learning how to find derivatives of inverse trigonometric functions. We'll start by reviewing inverse trigonometric functions and see how to find their derivatives, and then walk through some example problems where we can practice applying the derivative formulas. Be sure to download the free guided notes to follow along and work through the examples with me. We're going to begin by reviewing inverse trigonometric functions because I know these might be rusty from when you studied trigonometry, and then we're going to find their derivatives. I have written down 3 triangles, and in each triangle, x is either equal to sine theta, secant theta, or tangent theta, because we're first going to find the derivatives of the inverse sine function, inverse secant function, and inverse tangent function. Let's look at our first triangle. The sine of theta is the opposite side over the hypotenuse, and that is equal to x over 1. This means that theta is the inverse sine of x, and that's the function that we want to find the derivative of. Notice that inverse sine of x, or you can call it arcsine of x, is equal to theta, and theta is an angle. So all inverse trig functions are just angles. Let's now look at our second triangle. Here's theta, and we can say that secant of theta is equal to the hypotenuse divided by the adjacent, and that's x over 1. So if we solve for theta, we get that theta is inverse secant of x. We're going to do the same thing down here for our third triangle. There's our theta. And for this triangle, we are going to find tangent theta, which is the opposite over the adjacent. So that's x over 1. And we get that theta is inverse tangent of x. We are now going to use these 3 triangles to find the derivative of these inverse trig functions. I am going to walk through the derivation of finding the derivative of inverse sine x, and then you can use the same method to find the derivative of inverse secant x or inverse tangent x. We're going to let theta be inverse sine x, and I recopied that first triangle over here on the right, and we want to find d theta dx. We want to find the derivative with respect to x of inverse sine x, so that's just going to be the derivative of theta with respect to x. So let's start by looking at theta and see how it relates to x. We can see that the sine of theta is equal to x over 1, so we're going to begin with the sine of theta is equal to x. To find d theta dx, we are going to differentiate both sides of this equation with respect to x. So we're going to take the derivative with respect to x of the left-hand side, sine theta, and the derivative with respect to x of the right-hand side, which is just x. The derivative of sine theta is cosine theta times d theta dx, because theta is a function of x. And then on the right-hand side, we just get 1. So this tells us that d theta dx is 1 all divided by cosine theta. Now we're going to go back up to our triangle and figure out what cosine theta is. Cosine theta is the adjacent side divided by the hypotenuse. So our cosine theta is just the square root of 1 minus x squared. So we just found that d theta dx was 1 divided by the square root of 1 minus x squared. So that tells us that the derivative with respect to x of inverse sine x is 1 divided by the square root of 1 minus x squared. You can use the same method to find the derivative of inverse secant x and inverse tangent x. Let's now look at all of our formulas combined. I have written down a table with the derivatives of all 6 inverse trigonometric functions. On the left, we have the derivative with respect to x of inverse sine u, inverse secant u, and inverse tangent u. And then on the right, we have the derivatives of inverse cosine, inverse cosecant, and inverse cotangent. Notice that the derivatives on the right-hand side are derivatives of functions that all start with a c, and they have a negative sign included in the derivative. It's nice that the derivatives on the right are just like the derivatives on the left, so if you have to memorize these, you really just have to memorize the 3 ones on the left-hand side. And this is the part that you really have to memorize, because all of them have a 1 in the numerator. Let's now go over some examples. In each of these examples, we are going to find the derivative of the given function. In our first example, our function is y is equal to the inverse tangent of 4x quantity squared. On our left-hand side, we have dy dx. And to find the derivative of the right-hand side, we are going to use the power rule. So we have 2 times inverse tan of 4x to the 2 minus 1, which is just 1, times the derivative of what's inside. So let's just write down, we're going to be taking the derivative of inverse tan of 4x. Over here on the right, I'm going to write down that the derivative with respect to x of inverse tan of u is equal to du dx on the top, and on the bottom you have a 1 plus u squared. Let's now go back to our equation and put in that formula. On our left-hand side, we still have dy dx, and then on our right, we have 2 times inverse tangent of 4x. And now we're going to take the derivative of inverse tan of 4x. This is our u. So we're going to take the derivative of 4x, which is 4. And then in our denominator, we're going to have a 1 plus u squared. So this is 1 plus the quantity 4x squared. Let's now combine our constants. So we have an 8 inverse tan of 4x. And then in the denominator, we have a 1 plus 16x squared. And that's our answer. That wasn't too bad. Let's now look at our second one. For our second example, we are going to be taking the derivative of the inverse sine of 3x plus 1. Let's go ahead and write down the formula for the derivative of inverse sine. So the derivative with respect to x of inverse sine of u is du dx on top, and then in our denominator we have the square root of 1 minus u squared. So our derivative is dy dx is equal to the derivative of u. This is u, 3x plus 1, so the derivative of 3x plus 1 is just 3. That goes on the top. And then in the denominator, we have the square root of 1 minus 3x plus 1 squared. We could multiply out our denominator, but it's standard to just leave it in that form. And we'll highlight this because that is our final answer. Let's now look at our third example. We are going to take the derivative of the function y is equal to x times inverse secant of 2x. On the left, we are going to have dy dx. And then notice that we have two functions here on the right. We have an x and we have an inverse secant of 2x. So we are going to use the product rule. So this is the first times the derivative of the second. So I'm just going to write this as the derivative of inverse secant of 2x plus the second, which is inverse secant of 2x, times the derivative of the first. The derivative of x is just 1. Now let's go ahead and let's write down our formula. The derivative with respect to x of inverse secant of u is du dx, all divided by absolute u times the square root of u squared minus 1. I always tell my students the one way to remember this is if the u is here, it's also here, and you have u squared minus 1 instead of 1 minus u squared. I don't know if that's going to help, but hopefully it will. So we have dy dx is equal to x. Now we're going to take the derivative of inverse secant of 2x. The 2x is our u. So we're going to take the derivative of 2x, and that goes on top, so that's a 2. And then we're going to divide that by absolute 2x times the square root of 2x squared, so that's a 4x squared. The absolute goes away because we're squaring it, and then we subtract 1. It looks like our 2's can cancel, so we're going to write this as x divided by absolute x square root 4x squared minus 1. And we did it. There is our final answer. And that's it. You learned the derivative formulas for all 6 inverse trigonometric functions and practice applying them to different types of problems. To really master these derivatives, make sure to work through plenty of practice problems on your own. If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.